Welcome students. In the previous video we have seen about the eigenvalue and eigenvector problem for a square matrix. In fact, we have found the eigenvalues and eigenvectors of 2 by 2 matrix. Now in this video let's talk about the diagonalization process. Okay? We will see what is the definition of diagonal matrices and if possible we will if a square matrix is diagonalizable we will find the diagonal matrix too. Okay, now to define something called as diagonal matrix, diagonalizable matrix, we need the definition of similar matrices. So let me first put a definition of similar matrices. Similar matrices. Now two matrices A and B are said to be similar. Of course, they have to be of same size, square matrices. So two matrices, two definite square matrices the A and B are called similar if there exists an invertible matrix. Invertible means so there exists an invertible matrix say P such that we can write B as P inverse AP. So if there exists a matrix P which is invertible such that B can be written as P inverse AP, then we call A and B as similar matrices. Okay, you can check whether this is equivalence relation. That means check whether it is reflexive, symmetric and transitive relation. Okay, let us do it in a rough part. Now this is a reflexive relation. For reflexive we need to show that A is similar to itself. Now of course A will be similar to itself because we can write A as A here, and what will be that invertible matrix? So that we will have here that P inverse AP, and of course that invertible matrix will be identity matrix. So A can be written as I inverse AI, and hence A is related to itself, that is A is similar to itself. Now for symmetric, if we have A related to B, that is A and B are similar, then we need to show that B and A are similar. Okay, so if A is symmetric to A is similar to B, we can write A as there is some P invertible matrix, so P inverse AP, so BP. Now question is, can you write a B as some invertible matrix times A, that matrix? Okay, and for transitivity you assume that A is related to B, B is related to C, and with this you check whether A is related to C. In that case we will have the equivalence relation, and then you can define the equivalence classes too. Okay, equivalence classes that will partition the whole set. Let me not go into that, it is not interested in. Let us complete this part. Alright, so two square matrices A and B are called similar if there exists an invertible matrix P such that B can be written as P inverse AP. So now we will define our definition of diagonalizable matrix. Diagonalizable matrix. N by N matrix, of course square matrix, N by N matrix, the A is diagonalizable if A is similar to a diagonal matrix. That means there should exist a diagonal matrix. We know what is diagonal matrix. We have entries on all the entries of diagonal entries are 0. So only the entries on the diagonal may be non-zero. Okay, like it's identity matrix. Like identity matrix on diagonal, it may have any other value, it need not be 1, but of diagonal entry has to be 0. That is a diagonal matrix. Okay, so if there is a diagonal matrix and if there is a invertible matrix P such that we can write A as P inverse some diagonal matrix P, then we say that this A is diagonalizable matrix. Okay, so that is, we can write that is A is diagonalizable if there is a invertible matrix P, if there is an invertible matrix P, invertible matrix P such that P inverse AP is equals to a diagonal matrix, is a diagonal matrix. Okay, so if we can find that diagonal matrix and if we can find that invertible matrix, then we can find the form, that is P A is equals to P inverse dP. Okay, now of course not all matrices are diagonalizable. Okay, there are some matrices which are not diagonalizable. As a simple implication, we can show that if we have a diagonal matrix, suppose we have a diagonal matrix, then is it diagonalizable? Let me ask you, is diagonal matrix diagonalizable? Just understand this. For example, identity matrix, is it diagonalizable? Okay, we can check that. Now the thing is like we have a result which says A is diagonalizable if and only if it has n linearly independent eigenvectors. Of course, I assume that the learner has enough knowledge of linearly independent and linearly dependent vectors. Okay, so with this, I'm not going to prove the theorem, but let me just state the theorem. We will use this theorem. An n by n matrix, the A is diagonalizable if and only if, this is if and only if statement, if and only if A has n linearly independent eigenvectors. So if A has linearly independent eigenvectors and linearly independent eigenvectors, then A is diagonalizable. And if A is diagonalizable, then it has n linearly independent eigenvectors. Okay. So to check whether A is diagonalizable, you can check whether it has n linearly independent eigenvectors. So if a matrix does not have n linearly independent eigenvectors, then we can say that the given matrix is not diagonalizable. Okay, and just as a proof of this, we have the procedure to get how to get that diagonal matrix and how to get that invertible matrix P. Okay, so let me just give it as a remark, and we will use that remark to find the diagonalization process. Okay, so if lambda 1, lambda 2, say up to lambda n are eigenvalues of A, and let us take and x1 bar, x2 bar up to xn bar be corresponding linearly independent eigenvectors, then we take P to be a matrix whose columns are these eigenvectors. Okay, so P will be x1 bar, x2 bar, xn bar. We take this P to be the column vectors, and the diagonal matrix D will be the matrix whose diagonal entries are the corresponding these values. So it will be lambda 1. So if you are taking first eigenvector to be x1, then the first entry on the diagonal will be lambda 1. Then we'll have lambda 2. Likewise, we'll have lambda n, and off diagonal entries all are 0. So to get the diagonal matrix, to get this invertible matrix, this theorem proves very handy. The diagonal matrix will have all the eigenvalues on the main diagonal, and the invertible matrix P will be with the eigenvectors, corresponding eigenvectors over here. Okay, so to show that some matrix is diagonalizable, and to show that it has to get the eigenvalue D, sorry, to get the diagonal matrix D and invertible matrix P, we will use this result. Okay, so let us take one example. Let us take one example and example. So that the matrix A is diagonalizable let me write the matrix A. Let us take 2 by 2 matrix for simplicity. So A is equals to minus 2, 2, 2, 1. Okay, and find a matrix P and matrix P such that P inverse AP is diagonal. Okay, so for that we need the eigenvectors, we need the eigenvalues, and using these eigenvalues and eigenvectors we will have the matrix. Okay, so for this let us find the diagonal matrix, and let us find the matrix P, and then we can verify. Okay, now solution. First, find the eigenvalues and eigenvectors of this matrix. Okay, find the eigenvalues and eigenvectors of this matrix. So to get the eigenvalues, let me solve this completely. To find, let's for simplicity, let us use the previous result. We know what are the eigenvalues and eigenvectors. Okay, so rather to take your time, let me take the matrix which we already solved earlier. because we know what are the eigenvalues and eigenvectors. We already solved that example in the previous things. See? This is what the problem was. Another result, it says if we have distinct eigenvalues, if a square matrix A has distinct eigenvalues, then corresponding eigenvectors are linearly independent. And if the corresponding eigenvectors are linearly independent, then the matrix is diagonalizable. Okay, so let us take this matrix itself: 2, minus 12, 1 and minus 5. Its eigenvalues we already found. We got it as minus 2 and minus 1, which are distinct eigenvalues, and of course distinct and real eigenvalues. And for finding the eigenvectors, we have already proceeded. We have found these eigenvectors to be, say, 3 1 and 3 1 and 3 1 and 4 1. Okay, so let us use the same matrix. That will reduce our time on solving it. So okay, let's take the same matrix. We have 2, minus 12, 1, minus 5. We already solved this. Okay, so this has eigen values. Lambda 1 is equals to I guess we have taken minus 2, and lambda 2 is equals to minus 1. If it is ulta, then please do the respective changes. Okay, the corresponding eigenvectors are the corresponding eigenvectors are, what we got is x1 bar is equals to 3 1, and x2 bar is equals to 4 1 respectively. Okay, so this implies, using the remark, what we say is this implies the matrix P will be a matrix with x1 bar and x2 bar, and matrix a diagonal matrix D will be lambda 1 0 0 or lambda 2. That is, our matrix P will be equals to x1 is 3 1, x2 is 4 1, and matrix D, which is diagonal matrix, is minus 2 0 0, and this will be minus 1. You can check what is P inverse AP. Okay, for matrix A is to be written as P inverse dp. Okay, or you just check the procedure whether P inverse AP is equals to diagonal, either this way or this way. Of course, as a symmetric matrix, we have seen that this similarity relation is equivalence relation. Okay, we prove it. So it can be either this or this. You need to verify, then you can verify that. For example, what is P inverse? You should know how to find the inverse of this matrix P. We need P inverse. So check what is P inverse. Then multiply P inverse this diagonal matrix D and P and check whether you are getting A. Or secondly, you multiply P inverse, you multiply A and P and check whether you are getting this diagonal matrix. Okay, and this is the procedure. So let us recall what we have done, what we have to do. So thing is, we need to find the diagonalizable. You need to check whether the given matrix is diagonalizable. Okay, so let me write the statement of one of the theorem which I stated, that may be helpful for you. Theorem: the eigenvalues, the eigenvectors corresponding, the eigenvectors corresponding to distinct eigenvalues are linearly independent. Okay, so if a matrix has the distinct eigenvalues, okay, then the corresponding eigenvectors are linearly independent, and if the corresponding eigenvectors are linearly independent, then we can show that the given matrix is diagonalizable. So if we have 3 by 3 matrix and suppose the eigenvalues are different, not equal, then we can say that the matrix is linear, diagonalizable. Okay, and to get this diagonalizable form, to get the matrix P and to get the matrix D, we take the eigenvalues and eigenvectors, we put diagonal entries of that diagonal matrix to be eigenvalues and corresponding eigenvectors for matrix P, and that's how we get the form of the diagonalizable. Okay, uh, you can check as I have taken the example, show that example you can try to solve this. You can try for 3 by 3 matrix as well, but here you need to find the eigenvalues and eigenvector, that is important. Okay, so show that or verify whether, show that A is equals to the matrix what I have taken earlier, so -2 2 2 1, so that A is diagonalizable, and find invertible matrix P and diagonal matrix. So you can try this. Okay. So with this we are done with this diagonalization process. Okay. So stay home, stay safe.